So everybody, thanks for being here. This is a great meeting so far. I really enjoyed the morning sessions as well as yesterday's. And when Sydney and Steve invited me to come here and speak about visionary perspectives, I really welcomed the opportunity because at the Pittsburgh Supercomputing Center, we've been really looking to democratize the convergence of high-performance computing and artificial intelligence. We've done a lot recently, and I'd like to share some of those developments with you, letting you know how they're impacting users across the country and even across the world, and where we're going with it. So the talk is in 4 parts. Just motivation, why we're doing what we're doing, our vision for doing this, the steps we've taken in the recent several years to make it a national resource, give you some examples of success, building on things that Steve showed us, and some of them are in fact related, and then a quick summary. So first of all, this is PSC's first time at this event. I enjoyed meeting Steve at HPC also because I didn't know about this organization before that. And so just very briefly, we're a joint research center of Carnegie Mellon University and the University of Pittsburgh, obviously in Pennsylvania. We've been around for 33 years now. We've stood up 21 HPC systems, and of those, at least 10 were either unique or the first of their kind in the world. We have a number of active research projects. Some of those I'll highlight here. We do nationwide education and training in HPC concepts and AI. We have rotating workshops in MPI, OpenMP, OpenACC, and Big Data and AI. Stanford's a regular participant in many of those. And we do a lot of networking. We do a lot of advising to industry. So echoing Steve's perspective from this morning, we came from an era where what we did was big data. We didn't call it that, but it was hard to deal with, but it was structured, it was regular. It was that column on the left. Things from instruments like telescopes and genome sequencers, and from simulations. Now we're also in the area on the right, where we have very large unstructured data. Things are multimodal. We're looking at text, images, medical records, different modalities for tissue samples, sensors from seals swimming around the ocean, you name it. And we need to bring those together. We have a very large national community that use our center. One of our challenges is we don't have a small set of applications we run. We have hundreds, probably thousands when you include all the user codes. And so we have to resolve that. When we were looking for a new system back in 2013 and 14, we were really looking at ways to create knowledge. Our common goal is that. And the way we do that is really by starting with data-intensive applications and workflows. Simulation is still important. People are still doing MD. They're still doing engineering. But more and more, we're seeing it being data-intensive. And then letting people have the tools to make it very usable, to democratize service, to let everybody on board, even people coming from just laptop environments, because many scientists are doing exactly that, and they have never used high-performance computing before. And then to give them the tools for scalable high-performance computing, AI, graph analytics, and large memory computing. Letting them go beyond the laptop to what they really like to do instead of what they can do. And one of the goals are on the right. It's really letting people couple applications in novel ways, letting them collaborate much more broadly, and letting them stitch these concepts together. We know there's a lot. I want to jump back to Steve's comment before. These slides will absolutely be available. Like Steve Oberlin said, I'm happy to share with the videos. It's big, but depending on what the organization can do, I'm willing to share that too. So every year, Stanford publishes the AI Index. And the AI Index is a look back at where the field is going. And if you're not aware of it, I encourage you to have a look. There are a lot of strong signals, and they've been getting stronger year by year. This is from the 2018 report that was released in December. And one thing we see is on the top left are publications. And the publications, the bottom curve is all publications. And then the middles are, purple is computer science, and the top is AI. And what we see is those are increasing much more rapidly than the rest. The same is echoed on the top, where the top is, no reflection, that's okay. The top is participation at these large conferences, the biggest of which is now NeurIPS. Last fall, the NeurIPS conference sold out in about 11 and a half minutes. And we don't see that in HPC. This reflects the excitement in the field. We also see that in the bottom right is machine learning course enrollment. We see that going up rapidly. It's at all the major schools now, including Carnegie Mellon. And the bottom left is a breakdown of AI publications by discipline, looking at different things like deep learning, natural language processing, and so on. And the fact is, this is all growing. We know this. We're in this field. And we had to design a system to deal with this. When the National Science Foundation came out with a solicitation in 2013, or maybe it was early 14, I guess it was, they wanted us to bring in people who've never used high-performance computing before. And that's a very broad swath. It's people in biology, computer science, the social sciences, economics, you name it. They have very high-impact research they can do, and yet they haven't had the resources. So back then, we designed a system called Bridges. We named that for 3 reasons. One was to bring in the people who've never used HPC before. The second was to really bridge AI and HPC together. And the third is because Pittsburgh, I hear, has more bridges, is second only behind Venice or someplace like that in the world. So our local community gets it. And we designed this in 2014. The way it worked was then a year and a half later, at 2015 November for SC, then there were many panels on how we converge high-performance computing and AI. And I was on many of these panels in many of our favorite areas, the main conference, Intel, NVIDIA, you name it. And my real pitch was, well, we know how. We're doing it. Come and get it. It's available for use. So this is what it is in a nutshell. It's a fairly large system. We really prioritized productivity and ease of use, recognizing that at this point, computing is essentially free, but the scientists and the smart people who can use it are the ones who are in very limited supply. We have about 29,000 cores. We now have 216 GPUs. We included an AI expansion called Bridges AI. My co-author on this presentation, Paula Buitrago, is directing that effort. And Bridges AI brings in an NVIDIA DGX2 for the ultimate pinnacle in scalable AI, and then a number of other 8-way Volta GPU systems to serve a lot of capacity. This is funded by the National Science Foundation. It's available completely free of charge for open research and education. And a lot of people can't accept that, but it's basically our taxpayer dollars of good work. Allocations are peer-reviewed, but they're free. And they're open to anyone in the US as the PI, and their collaborators. You can be overseas. No restriction on that. I won't get into a lot of detail on some of these other aspects because this is an HPC AI conference, but we have large memory nodes up to 12 terabytes, which are valuable for other things. This was the first deployment in the world of the OmniPath interconnect. We are very early recipients of the P100 GPUs, and the same with the DGX2. We received that in October. So moving on, this system was delivered by Hewlett-Packard Enterprise, and it's funded by the National Science Foundation. The overall project is currently at $20.9 million US dollars, so it's fairly substantial by NSF standards. One of the things we needed to make this system usable by the people who never used HPC before, these are people who don't know what command line is, they don't know what a scheduler is, they have never used Slurm, and they really don't want to. And why should they have to? So we prioritize a number of things here. One is interactivity. Students now expect instant feedback. They're used to these devices where you can do a search and you get immediate gratification. And why should they have to wait in a queue for hours or days only to find they made a mistake and have to start over? So we prioritize interactivity. We actually do this with Slurm behind the covers. but we set aside a pool of nodes for interactive use. We thought this would work, but time has proven out that it actually does. For example, when a course at CMU on deep reinforcement learning was reaching its end a year ago, Paula noted that we need to make sure these students don't get hung up on our machine, so we expanded their interactive pool. In that course, there were 260 students with accounts on Bridges in one PhD level course. And we expanded the interactive pool, we measured it, we saw what happened, and sure enough, not a single student had to wait for access. And that was our goal, to make sure they would all succeed in their final projects without having to wait. At the same time, because the system is of sufficient size and we manage it carefully enough, we've also maintained it at well over 90% utilization. That wasn't necessarily a goal, but it's a happy outcome that's higher than we expected. We support all the popular frameworks like Python, Anaconda, R, MATLAB at scale. MATLAB at 352 cores on 12 terabytes is pretty exciting for the people that use that. And letting people use all of this without changing what they do from their laptop really lets them scale their work up by orders of magnitude. It lets them envisage doing what they really want to do, not what they've been able to do. And that's key. We support the AI frameworks. I'll get into that a little bit more. We've recently begun supporting containers very aggressively. We've had that for a while, but now with the NVIDIA GPU cloud containers, users have found that to be tremendously successful, as have our staff, because picking those up is much better than building them ourselves, given the pace that all of these frameworks come out. We support full-time persistent databases for people who have to stand up, science gateways, and persistent services for whole communities, and so on. Of course, a lot of software. And the elements in green, excluding the bottom, are things you can't find on traditional supercomputers. We haven't had those on previous systems of PSC. People have asked for them, but these are new.
What types of virtual machines are you using?
So the virtual machines, the question is what kind of virtual machines are we using? Under the covers, they're mostly KVM, and we mainly use virtual machines now for being the backends to persistent web services and gateways, like we have a Galaxy gateway and some others. Things are community portals that have to be up 24/7 and always running. For most application codes, we're mainly using containers. Going into the project, we weren't sure if people would want to spin up VMs in an elastic sense. And in fact, we didn't find any demand for that. People wanted it for persistence only. A good question. So conceptually, the cartoon of the machine is like this. Central to the whole thing is the interconnect. That's OmniPath, it's in blue. The point of that is it brings all storage to all compute equally. Low latency, high bandwidth. We designed the topology ourselves to be cost effective for these data intensive workloads and HPC applications at moderate but not extreme scale, because that was what that solicitation called for. We could have done it differently as well. A parallel file system is on that. There are now many parallel file systems. It has grown, as I'll detail. Management nodes, there are many small nodes for doing standard HPC style compute, dual socket Xeon. There are large memory nodes with 3 and 12 terabytes of RAM, respectively, 4 and 16 CPU sockets. And there's the new Bridges AI expansion that we just introduced in the fall that we'll go into. The real system looks like this. This is an interactive application that's at this URL. Feel free to grab it. It opens in any web browser, and it has details about all the node types, what they're good for. The blue bubbles indicate where all the parts of this machine are usable for AI and high-performance data analytics. And this is huge, because we really built this into every aspect of the machine, from the storage, through the fabric, through all of the node types, because all of them serve different roles in this. Real machine learning is not just deep learning, it's not just inference, it's not just pre-processing data and data cleaning, it's all of that. And people need all of them on one roof. They need to be able to go back and forth between these different applications and frameworks, and go back and forth between things like HPC with MPI, and TensorFlow and R, and in some cases Hadoop or Spark, and do all that in one place. We added Bridges AI, which is, I have not yet integrated it into the diagram, but when I have time I will, and that's down here. So I want to emphasize that this is all available for free for research and education. Also, by arrangement for corporate, we can make 10% of the resource available on a discretionary basis. That's on a cost recovery basis, which means we, by law, cannot make a profit, which is good for the users. And so that's a very good application for industry, for people doing proprietary work. The numbers here are startups on the left column. These are things you can get basically in a business day usually, just to get going immediately, to do some scoping, analyze performance. And for some projects, it's enough. Research allocations can be 100 times bigger in general. So millions to tens of millions of core hours, hundreds of thousands of GPU hours. And that's, again, all free. Education, same thing. These are for courses. And we have over 100 courses using the machine across the country. I want to just emphasize interactivity is key here. With new communities, that's number one. People are not willing to wait for results. And by doing it right, you can mask it and still keep the system very busy. The frameworks are essential. People right now are coding in Python. They want Anaconda, R, MATLAB, Jupyter Notebooks. We serve things like Jupyter Notebooks and R through an on-demand interface just through a web browser. So it makes it very accessible. Gateways are these very important concepts. I want to give this as context. So these are basically HPC software as a service. There could be AI, there could be big data as a service behind them. But some of these, the gateway portal for the Galaxy Gateway, for example, currently has over 100,000 registered users. And these are in addition to our 7,500 users or purely Bridges users. All the databases we support, of course, is whatever people need, we can generally do. I want to jump into very briefly Bridges AI and say what that is. One thing I did not do was start my timer, so if someone could give me updates every so often, it'd be really good. So Bridges AI includes several things. One is at the top of the pyramid, an NVIDIA DGX2. That is for applications that require the ultimate scalability to 16 Voltas and or 512 gigabytes of GPU memory. And we're hearing more and more of those. Next are 9 Hewlett-Packard Enterprise Apollo 6500 servers. Each of those has 8 NVLink connected GPUs. And the reason for this split is think of it as a pyramid. Not everyone needs the maximum capability, but you have a lot of people who need capacity. They need to work, they need to scale their models up. Over time, we may get more people moving up, in which case, by then, we'll look for more maximum scale resources, which will also have evolved. This is fully integrated with Bridges, of course. It's allocated in the same free mechanism through Exceed, which is the national cyber infrastructure for allocating these resources. This expands our capability by about 10 petaflops of tensor arithmetic. And this addition, in fact, expanded the overall AI capability of the NSF Exceed program across the country by 300% in this one action. We also have staffing in here to help people scale their models, and that's really an emphasis here. It's not just running a bunch of single GPU apps, but it's to look at how can we help people scale to use 8 or 16 GPUs at once or more going across the interconnect and go even faster. That also is time to solution, improving the human's productivity. So I'm not going into a whole lot of detail on these. I want to put them up just for reference. The V100 GPU is the core of this. It introduces tensor cores, on-package HBM2 memory, and the NVLink 2 interconnect. And the interconnect really excites me because this goes back to the days of custom interconnects and really building HPC-style machines. This is key to scalable HPC. And this is different than just buying Volta instances in a cloud. This is a scalable approach. And Steve and I have talked about this, and this is like a marriage of the Cray genome into NVIDIA and really having a great interconnect in a custom AI box. Also, this has its own, it has the NV switch that I haven't addressed on that slide. Next, I just want to mention these capacity nodes, 8 GPUs each, hybrid cube mesh topology. Really nice for deep learning, very cost effective. Like the DGX2, these have onboard NVMe SSDs for very high bandwidth access to data for training. High-end CPUs for doing what they have to do. The DGX2 is bigger and better. So on here we have over 80,000 CUDA cores, over 10,000 tensor cores. It's a really exciting box, and we had one of the first ones out there. We had an early user program through November and December. Right now, today, we're finishing the user survey to learn what people accomplished, what scalability they got, what scientific advances they were able to achieve. So I'm looking forward to getting those results later today, downloading them, and pouring through them on the flight back. On these systems, we support all the major frameworks. As I said, the NVIDIA GPU cloud has been a huge win for this because it lets us capture all the new revisions of TensorFlow and the frameworks as they come out. Containers, Singularity is what we're using. What we do to make it easy for users is we get the Docker image from the NGC. We convert it to Singularity. We have a local repo of that to make it very easy for users. And what we've heard from them so far is they found it a wonderful environment to work in. One of the things we're doing, as has been noted, we have a lot of data, and AI is driven by the availability. So we're really championing the availability of large data sets. Just some examples, things like ImageNet, the Common Crawl at Amazon, the GDELT network analysis out of Google, and many others, a lot of medical data too that I'll get to. And these are really what drive the ability of AI to move forward. It's really looking at big data as a service and being able to host this. But hosting these in one spot lets people collaborate and ask questions they would never ask otherwise. It's great that people make these things like GDELT available out here and ImageNet out there, but until you have them under one roof, you can't actually start working with them together. So what we found on Bridges is an expanding ecosystem. We started the system here, a collaboration between Carnegie Mellon and Pitt around bringing machine learning to biomedical big data for lung and cancer research. Added another couple petabytes of storage. We wired that in. It became a valuable resource. That was a proof of concept. We then moved down to the Brain Image Library, which is a $5 million National Institutes of Health funded project. And that's about confocal microscopy data for brains. In that case, mice, rats, and marmosets. But it's a great resource. This needs a lot of AI to deal with it. Humans cannot deal with navigating 10 petabytes of brain data looking for relevant structures. That then expanded into a project we launched in the summer of last year, really. It started June 21st. No, I take that back. It's October 21st. It ended June 21st. Called the Human Biomolecular Atlas Program. This is a very ambitious project. It's funded by the NIH Common Fund. It's looking at single cell resolution data for all major tissue types in the human body. So this is single cell genomics, imaging, mass spec data, and being able to understand these and how they differ in humans, being able to do analysis across them. The map component is because we'll be able to do analysis across these tissues and these organs, regardless of who they come from. And of course, organs come in all different sizes. A kidney of one person is different from the kidney of another person, but yet be able to do analysis. That we estimate will grow to tens of petabytes, and for that we're looking at a hybrid on-premise cloud solution. I want to skip a couple of these slides and just move forward. The Brain Image Library, this is the hub map. I will note that for the hub map, we are actually working with Stanford on that. There's Mike Snyder, who's one of the leading tissue people in the world, who is here and providing data to this program. So some successes. One I want to jump into, which is really scalable AI. And many of you may have been aware of this at different levels, but every time I have to give a talk, there seems it's a new development in this project. So there's always updates. So a while ago, back in Pittsburgh, we ran this on Bridges. And this was strategic reasoning. It's essentially optimization of counterfactual regret. These algorithms are very scalable. They address reasoning where you don't have complete information, where your opponents are actively conspiring against you. The game here is poker. And you don't know what the opponent has. You don't know their strategies. This would compete against 4 of the world's top professionals. And these guys are very sharp. They have their own computers. They do their own analytics every night on the game. And they talk and they say, this worked, that didn't. They found holes. Initially, the betting in the world was 3-1 in favor of the humans. And this is real dollars by real gamblers. For the first several days, the humans were winning, as they expected. Then the AI, and this was like the AlphaGo Zero AI that learned just from the rules of the game. Before this competition against the top humans, they had never played against a human. But within a couple of days, it had realized what they're doing, it had closed those holes, and then the humans were hoping that they would be able to have a tie, as they did 18 months before on the smaller computer before bridges. Well, that lasted for only a couple of days. And then Labradas, which was the name of the poker AI, closed those holes too. And now the humans were hoping they could lose with no more than 95% statistical significance. That lasted for 1 day. And at that point, about partway into the tournament, 8 days in of the 20-day tournament, 120,000 hands, Jason Less, who is an extremely good player, just told me he just woke up every day demoralized, knowing he'd just go in and get beat hard again. Now, this is an example of an AI really learning and surpassing the best human expertise in an area where you don't have the training set because you don't have the complete data. This was awarded best paper at the NIPS conference. It had a companion paper in Science. And so it's all good. What's the key here? The key is using 19 million core hours of compute and generating about 2.6 petabytes of data. Now this has to be real time too, because it's playing eight hands in this tournament, and this is real time. These guys play fast. You don't play 120,000 hands by taking your time. And so what the professor behind this, Thomas Sandholm, told me was he needed HPC for this, because in a setting where you didn't have that kind of HPC connectivity, we had loosely coupled nodes, then he would never been able to serve the low latencies he needed, where he had 50 nodes per hand on this, and since he's reduced model to fewer nodes. But that's not the end of the story. In January, there was a story in Wired, and many, many other news sources across the world, that this has now been transformed into, well, we knew it had been transformed into 2 startups. One of these startups is Strategic Machine Inc., which brings these technologies to applications like these in medical treatment planning, stem cells therapies, auctions, economics, and so on. The second company is Strategy Robot, which is aimed at defense. Yep, got it, thanks. And the key here is that, in this case, the Pentagon's Defense Innovation Unit has awarded Strategy Robot $10 million over a 2-year contract to investigate deploying these sorts of algorithms for things of national interest. So this is a case of AI being really transitioned from academia and these toy problems that you do for benchmarks because you can compete against them, to something that has other deeper significance. One of the applications I want to really highlight in the Converged HPC and AI is this one. It's from Chris Wolverton at Northwestern University. And this is really material science. And Chris uses deep learning potentials to go beyond what we've been able to do in decades prior of computational materials science. He has found the first iron bismuth and copper bismuth compounds that are stable. He's found new forms of titanium dioxide, like down here. And the points of these are that these have applications in high-temperature superconductivity, in better photovoltaics, in catalysis for H2 production. And these were things that people have been looking at these for decades, and they never found them. And as other speakers, Steve has noted, these help us think out of the box. They help us find parts of space we have not explored before, and then these can be experimentally validated. And they're leading us to discoveries that were not made prior. Another example is from James Wong at Penn State University, who's one of the leaders in weather forecasting. And there are others in Oklahoma that we work closely with. But James is looking at these formation of these very vaguely comma-shaped clouds that signal the onset of extreme weather. And the point here is by finding those early, then you can increase resolution in that part of the modeling and simulation, let the resolution relax in other spots, and thereby improve your time to solution, improve your quality, improve your forecasting accuracy. And this is, in fact, a collaboration with a commercial weather forecasting service. Steve noted CMS as a huge driver of a lot of this. We're working with them too, and we have a workflow, again, very non-traditional, of them streaming data to bridges and being able to get turnaround from this. This is with the groups at Fermilab, and obviously there are a lot of AI applications that we'll be looking into in the future around this because it's just needed. One more example I want to give, I'm going to fast forward after this, I think, to some of the conclusions here, is this one on glioblastoma. Glioblastoma is an almost always fatal brain tumor. It's one where colleagues of mine at the University of Pittsburgh have deep expertise. Jinghua Liu has been looking at applying deep nets to the Cancer Genome Atlas, which is a compendium of many tumors of different types for different patients. And his hypothesis was that because tumors are around disruptions in cell metabolic pathways, and those are essentially evolved, that if you look at a neural network on this, you should be able to see some of those structures also evolve. And he looked at this and he trained it. He found that, first of all, on the first layer, when he was optimizing networks to the data, that the right number of neurons in the first layer was about 1,400, which maps very well onto the number of transcription factors in the human genome that are known. And on the third layer, because now he's looking for things that he recognizes, in the third layer, he found a cluster that exactly maps onto this glioblastoma multiform, including methylation that, in fact, is not in the original data that can be inferred from the results of who had which kind of tumor. And that's really exciting because it means that in the data that you get out of this network and its self-organization, the kinds of things where you're neural look from TensorBoard and see emergence of lines and corners and faces, here he's seeing emergence of clusters of genes that pertain to tumors. They can find one he recognizes, great. The real question is, of other clusters in that layer, what do those correlate to? And what kind of tumors are they? And what sort of medical insight is there that can be found by saying, okay, now we have this cluster, we don't know what it is, but what tumor might it be, and then what are the therapies we may be able to design to deal with it? So we have a lot of other work going on. I'm going to fast forward a little bit. Let me just say that, so we have a lot of work going on in text and speech processing, of course. I'll be happy to talk to you about this afterward. In economics and looking at the meaning of words in context. And that's really key to this previous one too. The point of this is you need a context. You can't just translate word by word or sentence by sentence. Because in this first example, use of the word green, how you translate that from English to Portuguese depends on whether green is just referring to color or golf. There has different meanings. And then in the context of whole conversations, that becomes more important. We have a lot of work, as Steve mentioned, on GANs, these generative adversarial networks. And this is key to augmenting data. And for data sets where we just don't have enough, where we have high noise, this is having great results, but it's also computationally very expensive. So we have a lot of this. We have people working at Carnegie Mellon on multi-resolution and being able to improve the accuracy of segmentation classification by actually looking at the resolution of the imaging and adapting the scale, hence this eta scale algorithm, to be able to refine the accuracy, let's say that middle row, from being able to misclassify this bicyclist's arm as a dog to actually being able to get things right by adapting the scale of these images. Come back, please. Thank you. We have other projects, a lot of things going on with people who've never used HPC before. These are people in things like architecture, as in civil architecture, not computer, and be able to look at what's happening in public spaces. This is a public space in Pittsburgh called Market Square. Looking at the way people and objects move, everything from pedestrians to bicycles to umbrellas, and then being able to understand the use of that space and optimize for it. Okay, I just want to skip that video, even though it's fun. I want to put in one plug for a conference we are holding that I think would be relevant to some people in this room. This is called Artificial Intelligence for Data Discovery and Reuse. This is a National Science Foundation funded conference. And it really is looking at how do we federate data. Right now we have data sets all over the world. Using AI well is about data. But right now they really are siloed. There are data sets around the brain image library and the human biomolecular atlas, like I mentioned. There are others around many other domains. Different countries have stood up their own. We really need better tools to be able to discover that data. Google Dataset Search is one move in that direction, but it's limited. We're looking at more broad ways. We're looking at data privacy and reuse issues, ways to make the best of this, especially in the life sciences, but also more broadly. This is a conference we're holding at CMU in May. Please check out this website if you might be interested. We have a set of great keynote speakers, our own Dean of Computing Science, Natasha Noy, who's behind Google Dataset Search, and others. So if you're interested, please, our deadline for abstracts is next Friday, so it's good timing. Bridges have won a bunch of HPC+AI awards, just noting that the things we've been talking about here have actually received worldwide recognition for their value. So, summary, it's free, it works. Contact me if you want access.
Would you take a question?
Of course, I'll take anything you want.
Monday before last, Google invited me to a presentation by a Palo Alto Networks company called Dasher, where they announced that they're supporting Python 3.7 in their cloud functions, which I think is exactly what your Jupyter Notebook people need to go to avoid the Docker, NGC, container, rancher, singularity thing that they really aren't familiar or comfortable with. Do you support cloud functions, and do you have plans to do Python?
Well, we already do Python. Yeah. Yeah. We already do Python. As of this morning, we have Python 3.6.4. We just haven't installed 3.7 yet. But yeah, we absolutely do Python. And that's essential. Yeah. You get,
Do you have any measures of how many data scientists are using multiple GPUs versus one share of the GPU?
That's a great question. The question is, do we have measures of how many people are using multiple GPUs rather than one? Or shared. We do have those. I don't have them with me here. Get me your, let's exchange emails. I'll get those to you. Yes. Well, the question is, do we only target the cloud or do we also target supercomputers? I often describe Bridges as a new kind of supercomputer. National Science Foundation asked us to be able to support moderate scale HPC up to around 1,000 cores. So we support that kind of traditional supercomputing on Bridges up to 1,176 cores. We could easily have gone bigger. That's just what NSF wanted, so it's what we built. So the answer is yes to all of that. This really can be scaled to a capabilities class supercomputer easily. It can also be support much more of the cloud sense, and those can be done, and they are done under the same framework. Okay, if there's nothing else, be happy to catch me later.